Welcome to The Explainer. Today we're diving deep into the actual, physical, glass-based infrastructure that secretly powers the modern internet. It's so easy to just think of our digital world as this magical thing floating in a wireless cloud, but the reality is deeply physical. It's buried underground, it's stretching across ocean floors, and today we're decoding exactly how that works.
Here's our roadmap for today's explainer: light as digital data, the physics of fiber, photons versus legacy copper, overcoming distance and distortion, dark fiber control, and finally, the quantum fiber future. All right, let's get right into it.
Section 1. Light as digital data, encoding the internet. Let's lay down exactly how we translate everyday human communication into a literal beam of light.
I mean, it kind of feels like magic, right? You speak into a phone or upload a video, and boom, it crosses an ocean. But sending all that complex data really boils down to a concept as beautifully simple as flashing a flashlight in Morse code. Just, incredibly fast.
To pull this off, engineers use a really neat process called pulse code modulation. Picture a smooth, curving analog sound wave. First, they chop that wave up into discrete little sections. Then, they approximate the wave's amplitude, or its loudness. So say we're using a 4-bit system, we'd get 16 possible values for that loudness. If a specific section's value is, let's say, 10, it gets encoded into a binary sequence, 1010. So instead of a continuous physical wave, we now have a sequence of ones and zeros organized by time. And here's the cool part. We literally flash a laser to send that exact sequence down a cable. A flash is a 1, darkness is a 0. Simple as that.
Moving on to Section 2, the physics of fiber, the glass medium.
So our core focus here is this. Fiber optics use pulses of light to transmit data through thin strands of ultra-pure glass or plastic. That's the whole ballgame right there. We are completely ditching electrical currents and instead capturing photons to fire them right through this pristine physical medium.
Take a look at the anatomy of an optical fiber. Right at the center, you've got the core, which is usually made of pure silicon dioxide. Wrapped around that is the cladding. Now, engineers actually add elements like boron or germanium into this cladding to slightly decrease its refractive index. That basically just means it changes how much the glass bends the light. And finally, you have the outer buffer coating acting as a protective sheath so that fragile glass doesn't succumb to crushing, contamination, or moisture.
Now, you might be wondering, why doesn't the light just leak out the sides of the glass? Well, it all comes down to Snell's law and a really cool phenomenon known as total internal reflection. Because that core has a slightly higher refractive index than the cladding, when light hits the boundary between the two at a very specific angle, the critical angle, it doesn't pass through. Nope. Instead, it reflects perfectly inward. Literally no energy is lost to refraction, meaning that beam can just rapidly bounce its way all the way down the cable.
And the manufacturing process, it's wild. To make these long, microscopic glass strands, engineers heat up a large glass preform inside drawing towers that are literally several stories tall. That massive vertical drop allows the glass to cool as it's pulled onto a wheel at a blistering 1,600 meters per second. Honestly, it's a breathtaking feat of engineering.
All right, Section 3. Photons versus legacy copper. Light versus electricity.
The fundamental difference we're talking about here is electrons versus photons. Legacy copper cables, the holdovers from the old telephony era, rely on the flow of electrons. That makes them incredibly vulnerable to resistance and electromagnetic interference, or EMI. If your copper cable runs too close to a power line, a big motor, or even just fluorescent lighting, it can induce noise and completely corrupt your data. But fiber uses photons. Because we're talking about light traveling through glass, it is absolutely immune to external electromagnetic noise. It's a total game changer.
Section 4, overcoming distance and distortion, hurdles over long hauls.
So, over massive continent-spanning distances, light does face 3 major hurdles. First up is attenuation. That's just your basic signal loss caused by microscopic impurities or scattering. Second is dispersion. See, because different light rays can take slightly different amounts of time to travel through the fiber, your crisp digital pulse can actually broaden and smear out over time, which really bottlenecks your bandwidth. And the third hurdle is nonlinearity. When you pump super intense light through a cable, the refractive index actually shifts based on the beam's intensity. This can cause self-focusing or pulse compression that completely distorts those pristine ones and zeros.
To tackle these hurdles, especially that dispersion issue over long hauls, engineers manipulate a propagation parameter called the V-number, or normalized frequency. By shrinking the fiber's diameter to create what's called single-mode fiber, they keep that V-number below a specific cutoff. What this does is allow only the fundamental mode of light to propagate, totally preventing those mismatched transit times. It is incredibly efficient. Actually, by using single-mode fiber, intercontinental cables like TAT8 can push a signal a stunning 50 kilometers before needing any amplification whatsoever.
Which brings us to Section 5, Dark Fiber Control, owning the network.
Look, a lot of major organizations just don't want to share bandwidth or be boxed in by a commercial carrier's tech limits. So what do? They lease unlit, completely unused fiber optic cables directly from providers. This is a practice known as leasing dark fiber. Once they've got it, the business lights it up using their very own optical networking equipment. This gives them absolute, carrier-independent control over routing, quality of service, and encryption. And the absolute best part? If they suddenly need more bandwidth, they just upgrade their own equipment at the endpoints. They don't have to lay a single inch of new cable.
And finally, Section 6, the quantum fiber future, the next frontier.
We are officially entering the realm of the quantum repeater. To distribute complex, ultra-secure quantum keys over thousands of kilometers, researchers are designing all-optical memory stations. But instead of using traditional physical memory chips, they use circulating loops of fiber optic cable. By applying highly advanced error correction techniques, they can literally trap single-photon data inside these loops without losing it. It basically creates a tiny waiting room for quantum data until the next segment of the network is ready to receive it. Mind-blowing stuff.
And right at this exact same time, other researchers are asking a crazy question. What if we just ditch the glass core entirely? Welcome to the dawn of the hollow core era. Engineers are moving way beyond the assumption that we absolutely have to use solid silica. By designing hollow core anti-resonant fibers, they're achieving data transmission that is completely free of those nonlinear distortion effects we talked about earlier.
Which leaves us with the fascinating final thought for this explainer. Over the last few decades, we've essentially conquered the globe by mastering how to shoot encoded laser pulses through solid, ultra-pure glass. But if we can successfully transition to hollow core fibers, how will our networks, our economies, and really, our entire world change when our data isn't transmitted through glass, but at the pure, uninhibited speed of light in a vacuum? It's a thrilling frontier for sure, and one we're definitely going to be watching closely. Thanks for joining me on this explainer, and keep learning.